So, yeah, my name is Henrik. I work for MongoDB. This talk isn't particularly about MongoDB. I work on our performance testing team. So this talk is about how we tested different Amazon configurations to learn how we could get repeatable test results while using a public cloud for performance tests. Previously, I have worked at MySQL and MariaDB, so I'm kind of a database person at this point. But I'm proud to say that I'm actually like a full stack engineer, because last year in the Linux kernel they have accepted a patch for a device driver to make my son's laptop webcam work. So when I was younger, I also contributed to Drupal a little bit. So. Let's move. Sorry, this is the wrong direction. So what I will be speaking about today, first I want to explain like our setup we use for continuous integration, where also the performance tests run every day. And then from there we can list some things which were like assumptions that were made by the people who built this system before I was on the team. And then in this talk, we will learn whether these assumptions were true or not. Mostly they were not. Then we will go through the method that we used to do our testing and the different results we got for tuning or configuring different I/O and CPU and network. So, in MongoDB, we use a system called Evergreen for continuous integration. So it's basically like Jenkins, but we felt Jenkins was kind of getting old. We have written our own system in Go, which is kind of fully focused on using Amazon for continuous integration. Whereas Jenkins is actually older than Amazon, so the ability to kind of dynamically launch hosts has been added later. So today, purely in MongoDB, we have like more than 100 different projects in Evergreen. So of course, each stable release of MongoDB itself becomes so. This ends up being about 400,000 hours every month that we spend on Amazon. In performance, our statistics are about 5% of all of this, so mostly it's correctness testing. On the other hand, in terms of budget, the machines we use for performance testing are bigger, so it's actually quite expensive. So from that point of view, of course, it's important if we spend a lot of money on performance testing that the results are actually useful and not just kind of random garbage. From a performance testing point of view, the typical Evergreen setup is that you have like the central Evergreen system, and then for each test it launches one host, which we call a runner, and then on this runner some tests are running. Typically in MongoDB, they are written in the Mongo shell syntax, which is JavaScript syntax. But for performance testing, we have two different projects, which is not relevant today, but one project is called Micro Benchmarks, where we actually have some physical servers, have nothing to do with Amazon. And there we run some single server, quite simple tests, actually quite similar, like using the Mongo shell JavaScript syntax. And then what we are talking about today is our system performance testing, where we actually deploy multiple Amazon servers. The biggest one, I think, is like 16 server cluster, when you have 3 shards. So basically, in this case, from Evergreen point of view, Evergreen will launch one relatively small host, and Evergreen thinks that it's running the tests on this host. But what we actually do then is we run our own scripts that we created in the performance testing team to launch more hosts in Amazon and run the benchmark against the real cluster with big servers. and then when we get the results back, we save them on this evergreen runner, and then they get reported back to the central system where they are shown as green and red boxes for test results. And in our case, of course, the reason we had to do this project in the first place was that the results were mostly kind of random green and red, and had very little to do with whether the performance was actually better or worse. One thing to understand in what my team is doing, we are primarily not trying to make MongoDB performance better. We are trying to prevent it from becoming worse. So we do regression testing, and what we would want to see is to get the same result every day. So as long as it's not going down, it's fine. If somebody makes performance better, that's great, but it's not my responsibility. But what we don't want to see is that performance goes up and down every day, and kind of for reasons unrelated to MongoDB itself. So this is the plot or the story of this talk is kind of like this movie. Sometimes in the movie you start with the last scene when the boy and girl are kissing, and then you kind of go back to the beginning to explain how you got to this point. So we did quite a lot of different testing and configuration. So to make it easier to follow, this is like a list of everything, including the results that we got. But at this point, I think it's good to list the assumptions that were built into this system. And then I will, like for each result that we get later, I will then come back to each of these points to point out that which one was relevant for each configuration and test result. So one of the things, if you want better performance, or I suppose also more predictable performance in Amazon, Amazon recommends that you can use a dedicated instance. So instead of like using a slice of some instance with virtualization, you actually get the whole physical box for yourself, and there are nobody else using this. So of course you have to pay more, but then you don't have to guess like maybe performance was bad because somebody else was also heavily using the system on the same day. It's completely my physical server. So we use dedicated instances, and we believe it gives us more stable performance. We have actually never tested whether this is true. Even like many months in the beginning of this year we spent doing this project that I'm talking about, we actually didn't test whether this is true. On the other hand, I don't think it makes it worse to use dedicated instances. So for now we are just spending this money. I don't know if it's actually helping us or not, but I don't think it makes it worse. Then you can use placement groups, which means if you are running a cluster, you can ask Amazon to say that I would like these servers to be quite near each other in a network topology. Maybe they are like in the same rack even. And we actually do use placement groups, but I learned a month ago that we use them wrong. So we have different parts of the cluster are not actually close to each other. So essentially we are not using placement groups. And I will fix that after our next stable release. We also were using only a single availability zone, or a couple, because we wanted to distribute the load a little bit, but for the same test, we were also always using the same availability zone, because we thought that maybe the guys in Oregon have bought different physical servers than the guys in, what is it, North Virginia or North Carolina, on the East Coast. So and then they are just selling them like with the same label, but they are not actually the same machines. So we were using just one availability zone, and this sometimes gives us actually like insufficient capacity errors if the one availability zone is full. And we have also not tested it, but I'm starting to believe actually this is not the case. So I actually think the performance across different availability zones is probably the same. So this is again a restriction that we have built into the system, and it's probably not giving us any benefit. But this is still to be tested. Right, so a very strong assumption was this is database testing. Many tests are very write heavy, write a lot of data to disk. So probably if there is some noise in the results, it has to do with the disk performance not being stable, and this is probably the biggest source of noise. It is a big source of noise, but actually it was not, like it was maybe at best half. So also other configurations unrelated to disk had a surprisingly large impact on write-heavy tests. This was very surprising to me. In the beginning, we are using SSD disks, the local or ephemeral disks that you can have on Amazon instances, because we thought SSD is fast and it's also like local, so variance is going to be low. This was not true. Then there was this assumption, I have also read this on the internet some years ago, that you can have, like, when you deploy an Amazon instance, they can be good or bad. Like if you are unlucky, you get instances on some very crowded area of the cloud, and then you have less performance than you would expect. And if you are lucky, you kind of get your own server, and you get actually more performance than you paid for. So at least when we are using dedicated instances, this turned out to be false. We actually had a lot of code then built into the system that was testing. When we deployed a cluster, it would run some simple smoke tests before running the actual MongoDB tests to see whether this is a good and a bad instance. And if the result was bad, it would shut down everything and deploy 16 new servers from scratch and then run the same test again. It could take like 30 minutes before it got a good result and started to do the actual testing. It was all a complete waste of time and money. It did nothing good. Yeah, we had one colleague who said Amazon has the I2 type of instances, which are really expensive. I think they cost like $3 per hour, and we need 16 of them. So you should just use those because their SSD disks are better than the regular ones that we were using on the C instance type. So then noise will be low. So in theory, he was correct. He was just like reading Amazon documentation and saying this type of server is better, we should use that, and kind of don't waste 2-3 months time to do this testing, because you're just going to come to the conclusion that I already know from the documentation. So actually he was wrong. He was correct in theory that those instances are better, and that's why they cost more. But actually for our MongoDB tests, they were not better, so we are still not using them today. And we would not have known this if we had not tested. And of course, the overall question was, is it even a good idea to use public cloud, such as Amazon, for performance testing? Maybe we should just buy lots of physical hardware and run all the testing on that. So it turns out, actually, you can use public cloud if you configure it correctly. It's actually not that different from using physical hardware. It's also not free of noise without these configurations. So most of the configurations we have been doing in the end are the same that we have been doing for the micro benchmarks, where we do use physical hardware. All right, so now I'm going to explain what we did to test Amazon itself for performance variability. So most of our tests, we run some queries against MongoDB, and in the end we get like average ops per second. So it's like one number, and this is the test result. So in a way, the tests are not so advanced that we would look at latency or some percentiles or something. Maybe one day we will get that far, but even to get this one number, which is an average over some minutes, we were having problem getting a useful and stable result. So to measure noise, of course, normally in regression testing, what we do is we check out a build of MongoDB today, or one commit from GitHub, compile it, and then we test that, and then tomorrow we compile tomorrow's version and test that. But now we were not interested in MongoDB performance. Rather, what if we lock the MongoDB version to, we use 3.4.6, I think. And we run the same test 5 times. In theory, we should get the exact same results. So of course that was not the case, but this is kind of the goal of this testing. So if we keep the MongoDB binary constant, we should be able to eliminate all the other reasons why performance has different results. And then, of course, related to this theory that that there are good and bad nodes in Amazon, we also wanted to do this 5 times. So we would shut down the cluster, then we would start a new cluster and run the same test 5 times again, and do this with 5 different clusters. So we end up with 25 data points for each test that we can then look at whether they are the same or not. They are not. To understand more of like the reasons why there is noise, we added also, in addition to the actual MongoDB tests, we added tests for each of the components in the system. So we used FIO to test disk performance. We used iPerf3 to test network performance. And then we just wrote some simple tests our own to do like multiplication in a loop, or to do like sleep 1 millisecond and things like that to see whether even the CPU performance is stable. And I can tell you it's not. And then, of course, the last question is, so when we say that we need to minimize noise in the system or noise in our results, so what is noise? And even this wasn't a simple thing to answer. Originally, we called this project Minimize Variance. But then when we started to think about what we are doing, we said we actually, like, variance is a specific statistical variable, and we actually didn't use variance then for any of our graphs or like metrics. So what we actually ended up using is we take all of these 25 results, and we take the maximum and minimum. So we kind of want all of the results to be below some threshold, whereas variance is more like the kind of central part of your distribution. And doesn't look so much at the tails. Then if we divide by the median value, you get a ratio or essentially like a percentage. So in most of the graphs, you can just see a percentage, and we ended up saying that if we can get below 10%, that would be great. Most users will not, if you like download and install a new version of MongoDB, and the difference is 7% in performance, you will not be able to tell whether it's because of MongoDB or it's because of whatever else upgrades you have done. So that's kind of okay amount, and it's difficult for us to get better precision than that anyway, just like it is for the end users. So the goal is to minimize this one formula. So once you have such a goal, it's easy to start going. We run all of our tests 25 times, like I have explained. Later there will be nicer graphs, but then when you get a lot of data to analyze, what I want to usually do is to plot very information-rich graphs, so I can look at the data many different ways. Eventually I ended up with a Python script that generates 400 of these PNG files, so this is the one that was most useful when I looked at all of them. What we can see in this graph, each line is one test. And as you can see, we have run it 25 times from 0 to 24. And on the y-axis, you have operations per second. And of course, in this graph, we can mostly see the test results that have the highest values. So there are a lot of tests where the ops per second is like 100 or 1,000. So I had then other graphs where I zoom into those as well. They look the same pattern as we see here. So now the question is, what can we learn from this result or from this graph? This was like a huge shock for my team and some of the people around my team that this pre-qualification script or smoke test script that we had been running that would delay the test for 30 minutes, probably waste like $50 of money trying to find good instances, was what I call witchcraft. So it's not based on science, it was just somebody believed something and he had written a script to do this, which did nothing. So if this theory had been true, what you would expect to see is that the first 5 points are maybe on this level, and then the next 5 points are higher because they are on another server, and then the next 5 points are again on some other level. But we actually don't see this pattern. Except for a few tests, it seems that the first test tends to be lower than the second and third and fourth and fifth. But in most cases, there isn't even that kind of variance. So basically, we see that each test result, there is a lot of up and down, but it's not correlated per server. So one of the assumptions was clearly false. This was like the first time we got test results, we said, oh, actually, that was stupid. So now we can remove this script and save a lot of time and money, made our life simpler, but we felt kind of stupid that this had been in production for 2 years without testing it. This is another information-rich graph to get an overview. We don't learn anything specific from this, but maybe on the next graphs this will give you some background. So here we have each test as one bar, and I plotted, so you can see lines. This is the minimum result, the median, and the maximum for each test. So each bar actually aggregates the 25 results, and on the top you can see if there is like a big hat, that means there was a lot of, there is like a big range between the minimum and maximum. And on some of the tests, actually the results are very repeatable. There is no variance. So then, actually, even for those tests, then is the question, why is there no variance? Maybe we are not actually stressing the test enough. So after we have done this kind of Amazon investigation, we realized a lot of our tests themselves were configured in a silly way. For example, what you can see here is a test we call insert vector, this one, where running with a single thread you get some performance. Running with 16 threads you get much higher performance, but running with 32 threads you get exactly the same result with 16 threads. And in fact it turns out that with 4 and 8 threads you will also get the same result as 16 threads. So the only benefit of running with 32 threads is that you get more noise. So later we have changed these thread levels, but for this project they were as they were. So basically also with the thread level somebody just had guessed 3 favorite numbers, and this is what we were running in production. All right, so after this we will look at graphs like this, where each bar is actually the percentage. So you take the minimum and maximum and divide by the median, and then you get the percentage. And what we want to see is that we get below 10%. Now this graph is actually not the MongoDB tests, rather here we have results for the FIO testing. We have 6 results for each type of Amazon configuration. The first 2 are read and write latency and this kind of noise metric. The second are IOPS, read and write, and the last is bandwidth, just kind of pushing megabytes through the I/O. What we can, the default we were using was C3 8X large with the local SSD disks. So what we can learn from this is that the local SSD disks are more noisy than any other alternative we could have chosen. So in a way it was not just like witchcraft, but the person who chose this was very unlucky. If I had chosen any other alternative possible, we would have had less noise than what we were getting in our tests. And interesting question is why? Here we kind of reach the limits of Amazon, because Amazon isn't really kind of always telling what kind of hardware is behind there. I think one guess that I am making, we often talk about these SSD disks as local disks, but actually that is not what Amazon says anymore. They are ephemeral disks. So what I think is happening is that we were paying for a dedicated instance where the CPU and RAM is dedicated to us, but actually the SSD is not on this hardware. It's maybe somewhere in the same rack or close by in the same network, and there are also other servers using the same SSD, and this is why it goes up and down. This is just a guess. We will never know the answer unless Amazon tells us. Anyway, any of these others, we actually get better, like less noise. In fact, for the, oh, sorry, the image is cut here. So the 2 last ones is using EBS with prioritized IOPS. And on EBS, yes, latency latency has quite high noise. But then for the IOPS, which is the most important one for us in most tests, is essentially 0. And then there was this, this other opinion about using the I2 or I3 instances. This actually has both low latency and not as low as the EBS alternative, but still kind of similar low level of noise for the IOPS and bandwidth. So based on this result, this guy was correct. This is kind of best if you look at the FIO results. Have I explained all of this? So SSD is false. EBS is bad, false. Just use I2 instances is true in theory, but when we go to the next slide and look at the actual MongoDB results, you see that if we just take the C3 instance we were using and switch to EBS, most of the tests are actually 10% or lower. So this is already, was kind of close to our goal just with the first iteration of tests, whereas with I2 we still have many tests which have, this is like 30% is the highest line. Sorry, the projector cuts a little bit here. Or actually, I think it's my laptop that has a wider screen than usual. I need to be careful with that in the future. So this is ultimately what we care about. And for all of the alternatives, they're not significantly better than what we already were using in production, except changing what we had to EBS with prioritized IOPS was actually better. So the lesson learned from here was, which again, you might say, well, of course, if you use prioritized IOPS, we use 5,500 IOPS, you will get exactly that. But I don't think that's like a conclusion you can just make. Probably what you would expect from Amazon is that this is at least a minimum value, but maybe you would sometimes get more. And for us, actually having more performance than we expect is just as bad as having less, because we want the repeatable results. But it turns out, actually, you get exactly 5,500 IOPS if you pay for that, because Amazon doesn't want to give you more than you pay for, I don't know, or they just have good engineers. So at this point, we have switched to EBS. Later I went back and looked at, so why actually, if this, like the disk on the I2 was so good, why are the MongoDB results so good? And it turns out because this is a bigger server that has more RAM, also the MongoDB cache, which is by default 50% of RAM, will be bigger. So this means the checkpointing becomes more difficult for the storage engine, which is why you start to see drops in, like periodic drops in performance or stalls in MongoDB, which we don't see on the C3 instance. So this is now like a thing in our backlog that we should actually start using this for testing, because it exposes some MongoDB behavior that we can probably improve. But for the purpose of this testing, it was a bad choice, because it would have given us more noise, not less. So we didn't choose it for this testing. So now we use EBS disks. And this is actually what our test results look in production. Each of these dots is 1 day. So it's like one commit in the MongoDB GitHub repository. And then for each day you get another dot. I don't remember what happened here. Maybe it was some regression or kind of like known, accepted regression because some feature changed. But here, as you can see, we have quite, these are the worst tests, different kind of heavy insert tests. Variances from 450 to 300. So 300 minimum, 450 is maximum. Essentially quite useless results. After we move to EBS, you can see that the lines are, like the variation is much tighter. So this was a great achievement. With just a few weeks of testing, we could deploy this into production. So then we went to look at CPU. We felt that we had already gotten quite good result with the EBS, so I wasn't very optimistic that this is going to make a big difference anymore, because I was also believing that probably the disk is the most important component. But it turns out you can actually, on modern servers, do quite a lot of tuning with the CPU because they have a lot of like power saving stuff and something. So some CPUs might be turned off or running with lower frequency than what the kind of specs it has as the official frequency. And then both in the CPU and in the kernel, there are configurations like what to do when things are idle. So we set idle to poll, so you kind of actively wait for something to do instead of going to sleep and waking up many milliseconds later to check whether there is something to do. Hyper-threading is kind of fake CPUs, so you get a little bit of extra performance, but what essentially happens is that you have two threads running on the same CPU, so they will block each other, and this adds, again, randomness. So when we disable hyper-threading, we actually have more predictability for each thread. And then if we run all of, like the Mongodb process on, just pin them to the CPUs that are on the same socket, then you don't get requests for memory across the two CPU sockets, and also like cache invalidation and that kind of things. So this might also be a way to reduce variance that comes from CPU and RAM access. So we tested various various combinations of these, and what you see, so again, like on the first bar is now our like production variant, and then we turn off turn off these power saving states and sleep states and no hyper threading, and then we pin to a single socket, and there is, we tested still both C4 and C3 type of instances, and what you see is generally towards the right, the last result is typically the best, or in the top, close to the best ones. So the type of tests we did here, just kind of run some computation in a loop, but we were also interested, and this turns out to have a big impact, like what happens during, like if I call sleep, is it exactly 1 millisecond, or is it like 1 or 2 milliseconds? How exact is the sleep? So there is some variance. The variance is small, but there is still difference between the different configurations. This is the Mongodb results for a selection of tests. So the same configurations as in the previous results, which were the CPU tests. So especially here you can see that typically the last bar is better. So it means essentially that turning off all of these different features, hyper-threading, power saving, and not using the other socket at all, always gives us a little bit of better performance. What is interesting here is I have made the 5% line tick. So now we are mostly below 10%, except for some tests which still are problematic. But actually most tests, if you look at this green bar, are below 5%. So this is an exciting result, because it's better than I was hoping for. So an interesting one here is then, well, now it looks like the tests are pretty good. So why is, for example, an index build still has a lot of randomness, up to 25%, even with the green one, which is the best configuration? So then we went back, we were doing review sessions with some of the lead architects of the MongoDB server. So one thing we can see here is that for the insert tests, most of these are now insert tests that you see on this graph. They are still impacted by the CPU configuration. And it actually makes sense, because if you have threads that are blocked on waiting for I/O, then essentially it's the CPU who decides when they are sleeping. It's the CPU that will decide when they come back to do work. So in hindsight, this makes sense, but it was a bit of a surprise to me. All right, so why is the index build big on noise? We went back and said, well, didn't actually the Wired Tiger lead developer, Michael Cahill, tell us that index build in White Tiger is not predictable, because if some checkpoint is happening, it will not start an index build. It might start like 5 seconds later or 30 seconds later. So clearly, doing a test with index build, if the index build doesn't even start predictably, the result is going to be unpredictable. And once we added some, we added some additional MongoDB calls to make sure that the system starts from a quiet state. So then the index build test actually is predictable. We got great results. The same with the last 2 tests there that have quite a lot of noise. There were problems in the test at this point. So now we are in a state where actually we can achieve great predictability for our tests. We also did network tests. And there is quite a lot of variance there, especially if you look at the latency of network calls. And we tried, there's like a TCP low latency setting that you can set either in the application or in the kernel. Didn't really make a difference. But now we have realized that actually we are using the placement groups wrong. So probably this is a huge source of randomness in our clusters. So maybe I will look at this again once we use the placement groups correctly. So essentially didn't get much out of the network component. So now we deployed these CPU, improved CPU configurations to production, and you can see that the line becomes straighter again. And in most cases, you also see that the line goes down, because now we are using essentially just 25% of the CPUs we had before. Not really 25%, because hyperthreads are not real CPUs, but we shut down the hyperthreads, so now we have half the amount of CPUs, and then we use only 1 socket out of 2. So we only use 25% of the CPUs that we would have. But that's okay, because we are not here to maximize performance. We want to see a predictable line, and we achieved that. So this made everybody very happy. And this summer and this autumn, we had actually been able to catch a lot of regressions, because we finally have a performance testing system where we can get meaningful results. We then, after working with this project, we realized that actually we should take this FIO and CPU and iPerf tests, and we have added them to production as well. So in addition to the MongoDB results, each day we get this kind of dot also that records these, what we call Canary Tests. Because now this is kind of a check for when we use Amazon. This is a check that everything is still okay with Amazon. So if there is some regression in the MongoDB tests, I can go and see if is there also a regression in the FIO results. If yes, maybe this was like something happened with Amazon. If the FIO result and the iPerf results are the same, then probably it's a MongoDB regression. So this gives more insight into the cluster that was running the test, because the cluster is not the same from day to day. So this has helped us also to give more confidence in the daily results. So the final thing we have learned, because we had this doubt that maybe we shouldn't use public cloud at all for performance testing, it turns out actually it's great. Of course, you get the elasticity and other benefits of using public cloud. And I think at this point our results are just as good as we could get with physical hardware. And in fact, even if we had bought physical hardware, we would have to do the same exercise anyway to tune the disk settings, to tune the CPU settings. Like all of the CPU settings, for example, are the same for a physical machine. They have nothing to do with virtualization as such. I think it's exactly the time for questions.
Hi, my name is Zia, and
Hi.
My question is, where can I get your presentation?
Good question. Where is the mouse? Oh. There we are. I have like this presentation is in my GitHub repository. So if you go to henrikingo.github.io, there's a link to presentations, and the second presentation on that list is this one. Yeah, I will leave it like that.
Hi.
Hi.
I have a question. So, what about Intel Turbo Boosts?
Turbo Boost.
Yeah, is there a Turbo Boost on C3? And was that the reason that you weren't using C4 and C5?
Right. So yeah. So what remains a bit of a mystery? Why is C4 not equal or better to C3? Probably there are like more of these features that we should turn off, and maybe we didn't know of all of them, or maybe we cannot turn off all of them. So I don't know. Yeah.
Another question: what exactly was wrong with placement groups?
Sorry? The person who we used Terraform for the actual deployment of nodes, and the person who did the Terraform files put all of the data nodes in one placement groups, and all of the proxy nodes in another placement group, and the client in a third placement group. So they are like the client and the server are not close to each other at all.
Hi, thank you. You mentioned that you didn't have any improvements in performance when you switched from 16 to 32 threads or cores. What kind of test it was? Just
this is a batch insert, so you have like 1,000 documents and send them to the server as a batch. So of course, with a very low number of threads, you already saturate the server because each, like one operation is actually 1,000 operations.
Okay, thank you.
Yeah.
Hi, Henrik. Thank you for the presentation. So the question is that, so you mentioned a couple of times during your presentation that your goal is to minimize noise.
Yes.
But your customers probably want to get more performance and with low cost. So they have completely different goal, and they will optimize the hardware and operating system. So basically the environment, they will tune this cache, they will tune IO scheduler.
Yeah.
So how can you be sure that your tests actually matter because they have completely different goal and run in different environment?
Yeah, so of course, ultimately, this is what we want to provide. So I have also made the point in the team that now, like if you play hockey, for example, now we are just playing defense. So we are trying to keep our own goal safe, but we are not actually attacking and trying to make it better. Like MongoDB engineering in general is sometimes doing projects to make performance better, but we have very little testing to help them get there. But in a way, I do think like this is the kind of Italian style of football, that it's good to start with good defense and then you make one goal and then you win. So you are absolutely right. And like I said, for example, with this I2, but even then, like the C3 8th large is not a small server. So I think these are still okay for performance testing, but we already know that if we go and use the I2 instance, actually we will start to see these stalls. So we should definitely add this to our testing and tell the engineers to fix that.
Thank you, Henrik, for your presentation. My name is Sardar. You told in your presentation that network performance and network tests doesn't correlate with MongoDB performance. Also, you said that you used cluster wrong.
Yes.
So what is the conclusion? Does it really network performance not correlate with MongoDB performance, or your tests just doesn't cover network performance?
So yeah, so this is a good question. So the configurations we tried then, which was, for example, or maybe it was only this TCP low latency that you can set in the kernel, didn't make any difference. And when we did this in the spring, I had not realized that we are using placement groups wrong. So we thought that because we are using placement groups, we should have low latency and low variance in latency in the network. But now I know that we are using them wrong, so probably if I change it, we will get less variance. So maybe also that like the test variance will go further down once we do this. But I have not, because now we are in release candidates, so I don't want to do this change now. I will do it later.
Thank you for presentation, Henrik. One question. Probably I missed, but did you get reputable test results for different regions in Amazon? Or
yeah, we have not tested this.
You tested only one region.
We use 2 regions, but we don't compare them. We have slightly different tests in 2 different regions. Yeah.
Okay.
Okay, thank you for the talk. One quick question. Did you detect any time of day variance in your tests?
We have not analyzed this, but if you remember the first graph with 25 points, basically to me it looks just random. I didn't see any pattern at all.
And it was like for how many hours?
The tests are like 2 to 6 hours, the different
so
tests.
That's the whole suite?
Or just that run? There are a lot of, there are different tasks that can be run separately. So not all tests are run in one sequence.
Okay. So essentially the answer is no.
Probably no, but I didn't like specifically test that. Do you work for ClickHouse, by the way? Yes. We should talk.
Hello, thank you for the talk. You made an amazing slides.
Thank you.
Because they...
Right. I actually maintain this. This is an open source project, Impress.js.
Okay. I have a question. Do you use some monitoring for this thing?
For our performance testing?
Yes, yes.
Not yes and no. MongoDB has an undocumented feature that we use, like we created for our own support team. So in the MongoDB data directory, you will find a directory called diagnostic.data, which is a compressed file with a lot of statistics each second from the MongoDB server, and also IOStat and some other operating system statistics. And if you are a support customer, we will often ask you to just give this file, and then we have some internal tools to analyze it. And also for performance testing, we do check, for example, replication lag we can compute out of this data by comparing timestamps, and then if it's bigger than some value, we will actually fail the test. And we can check some other things as well, that the RAM consumption cannot be bigger than some value. But we don't. So if a test has failed, then some engineer will want to know more details what was going on in the server. Then he can use this data and use the same tools that our support is using with customers, which are actually not public, unfortunately. But you get graphs like in any other monitoring tool. But we don't, like the automated test does fairly simple checks. Like if some value is above some limit, then it will fail. Then a human can use graphs if he wants.
Тогда давайте поблагодарим нашего спикера, поаплодируем еще раз.
Thank you.